I also other than that, one more thing, if you end up needing energy, alright, I'm about to mesh, there are a lot of jars and mesh weight stuff up here. How often I can withstand rapidly repeated tests. But you can also do some other things to lighten that mass. Might be something that you need to stop and creative, to make that, not have so much, alright, other than that, good job, guys. Going good.
Doing videos like cooking with like cooking like she's like behind you like holding like on her shoulder like she's like behind you and your hands are backwards and then she's your hands so it's gonna be like hi girlfriend. So then it's gonna be like funny. I see those videos. It's like a girlfriend has hands.
So basically, we need to fix that. He said that
When I say,
and then he also said that how do we know if the rubber bands are just going to move by themselves? We don't know. So we can also just let the rubber bands move it if that's the case. Because we can also quit worrying about if the seesaw is going to be overlooked. Genius, that's a genius.
It's cute. It's not like the rest of them.
she totally smeared on my face.
Also, Cormac played this little prank and thought it was funny to set up a mouth trap in my face. He put it a mouth trap in here, and this like this, like this.
Because my things are buttons there's no
What the hell?
sorry, I was choking on my drink. Like I was actually like gonna die.
I'm Miles Singler. Yeah, so this is our design. We've got kind of a basic model. This is kind of janky. It's kind of just to exemplify some positions. It might be hard. The basic design is just kind of the arm swinging, catches the crab, and throws it up the ramp. To do this, we had to have the arm bigger than, to have the arm in the ramp, it was bigger than the back of the tables. We decided that we could just take the arm and just put a mousetrap there, and then that gave us the ability to just fold that arm in half. So when we started, it's just, we just push something, sets off the mousetrap, and that just swings out. There's a rope connected to the arm of the mousetrap, and that sets off another mousetrap that swings it around, catches the crabs, and throws it up. We have our very specialized arm, and we actually measured this and tested this a bit, but if we get it the right length, it will catch the big crab in an area, the small crab in an area, take them both, but due to the length of the arm, it actually works perfectly where the big crab will be thrown up the ramp and the small crab will not. It'll just be thrown off the side. So that's the basic works. One of our main problems is, and we didn't do that in here, we got this from our peers, is that the energy, because mousetraps are very like fast and stuff, is the energy might be a problem because we have it swing all the way up. So we decided that if, for some reason, because these are going to be made out of plywood, so if the mousetrap is way too fast, or sorry, way too slow, because the plywood weighs it down, then we planned for a wheel, just a CD wheel, that will pick it up like just slightly off the ground, and that will take off a lot of friction. And that's just if it's too fast, if it's too slow due to the friction, lock that one and it'll take almost all the friction off, and that will make it go a lot faster because it needs to hit the ramp fast enough for the mousetrap to shoot up it. We also have a plan because if the mousetrap is way too fast, I was worried that it might just shoot up, rebound off the wall, and just go down. Originally, we put this wall up because I was worried that it would just shoot up and fall off the other side. But if it hits the wall and falls down, we did purchase a exotic material, which was sandpaper, just so we could coat this top of the ramp with sandpaper, so that when the crab goes up there, the sandpaper will apply a lot more friction and slow down its movement, so that even if it will slide and then even if it rebounds, it almost definitely could not withstand that much friction and slide back down. So we just kind of were playing with friction just to make sure that any possible thing that could go wrong wouldn't. Let me see. We did measure everything out so that this would, and we can also, this fits about right within the boundaries. We can shorten this arm and lengthen this arm. It really depends on any challenges we find while actually creating this. From what I've seen, we've pretty much solved all our problems, but I know there's probably unexpected problems. This knot, if you actually tie a certain knot, it will tighten around the mousetrap, or you can just tie it to the holes inside the cheese. If you tie it with like fishing twine, it actually snaps really easily. So it does give enough force just to trigger the mousetrap, but then once it tightens enough, it just snaps really quickly, and then that gets it out of the way. That would mean that every time we test it, we would need to replace that twine or fishing wire thing. So whenever, okay, yeah. Next.
It just barely fits within the constraints. You can see the arm is like almost exactly the length of the ram from lengthwise. So that we're able to fit the crab.
This is our bill of materials, and the most abundant materials we have are the cardboard, aluminum, hardwood, and sandpaper. So the reason we have so much, the actual cost is $367. So the reason we have so much plywood is that we are actually accounting for extra plywood is that the cardboard which we're using to make the ramp, there's somehow an issue with that function. Maybe the cardboard gets put away or something. So we have accounted for extra plywood that pays for that. The cardboard with the plywood. And obviously with the sandpaper, which is exotic, we are paying actual market price for this, so this is not like cheaper by cent. So
I actually feel
sorry about
like I feel like we can do this. No, because this was like our only issue. We fixed this. Look.
and
And we
also,
did.
since we have extra, we basically want to buy
Our only issue is that
more
I go
than
from
or more hot juice with whatever we might. We have lots of materials, that's 100 grams. The second material on here is the mousetrap. We combine all of the 2 grams, which is not the weight. It's pretty light design, so if we needed to like substitute the wooden, we could probably.
Those things can be
Yeah, we would still need, we don't have like that much mass, like, we want flexibility in this regard.
Okay. Storyboard. I imagine a lot of you probably not reach most of a milestone. So can I have the story?
Bottom one switches sides.
Okay, so that's it. Pre-trigger, we are really cramped on space. That's why this whole thing is folded inward. start the contraption by pulling a string that activates this mousetrap, which extends the arm far enough to catch both of the crabs. And then the string, a string which is tied somewhere around here, activates this mousetrap because it's been pulled taut. And it catches both of the crabs. The small crab is in its own little spot, so that way, I'm sorry. When it goes to the ramp, the small crab is just kind of chucked off to the side, and the big crab has enough force to go up the ramp. And this is what it looks like in the end.
Oh, yeah, so this is kind of our energy. It's a little blurry. The pictures obviously are a little rough drawn about that. So this is just like our torque analysis. Really, it was really simple for energy for us because it was pretty much just we have two mouse traps. That's all the energy we have. We just set them off. And then we do have our friction analysis. So like I said, we're doing stuff to make that either less or more friction, depending, like less friction on the arm if it's too heavy and makes the mousetrap go slow, or friction on top if it goes too fast and throws it up too fast. And then also, I believe we calculated, what was it, like 1.6 joules of energy.
I think, because it's around about 8
Yeah.
yeah.
So it's really not that much energy. I'm really glad because with our plan, I don't think we're going to, it's not, I know we'll have to probably do some modifications, but I don't think energy is going to be one of them because our mousetraps are pretty just like, we just have the mousetrap and that's our source of energy. It doesn't really change. But that's just our potential energy. We don't have any gravity to take in. I mean, we've got, I guess like, yeah. But in terms of potential energy, it's really just the mousetraps that are preset. We are using the Max 2 mousetraps. So it's just those. And that's like our only source of energy, which makes it very simple. And simplicity is one thing that's good about our trap because really it's just kind of the three objects, the ramp, and then the two halves of the arm. And then we've got our mousetraps as our sources of energy. And that just makes it really simple and smooth. So any details that need to be ironed out, it'll be very easy to do.
Real quick question on your, go back to your manual engine video. You're gonna see this when Mr. Gonzalez created VR, this is your new VR, but this is not how we do it. So just let me guys know that. Your mass, change this mass in your torque, I wouldn't trust your torque. For example, you've got 2 square feet of plywood, and instead of, it's 1.8 grams, like look at the plywood line, and that's not how we do parts anyway. So 1.8 grams per square inch, and you're gonna tell me the whole thing, 2 square feet of plywood weighs 0.68 grams. That's not the same, okay? Somebody double check this, this is how you're up, like this is not gonna work. You're gonna have the same issue in your viewing as well. What I'd rather see is each part, you guys did each part design, right? So every part, which is the side of this arm, or making this piece, or making that piece, you have a lot of pieces to build. Your VOM shows every single part lined out, every line.
Okay.
All right, not just trying to sum up all the wood that we're gonna use, because then I don't know how you're gonna label that. Each part in your ISO, right? So this is some of those things. But if we had done that, we'd have a clearer idea. But that means that when you're doing your torque analysis, you can't tell me that whole long arm weighs 0.6 grams. It doesn't.
Okay.
It's not going to. So that leaves me wondering about some of the other stuff. Other than that, which is the big issue, since that is, the reason that's a big issue is because your whole design depends on that You get it done? And we gotta think it through enough to say friction's gonna be an issue, so we got some solutions around that. But other than that, I think that's the only thing. Everything else, though, good job, so let's keep going. All right, next up, let's do 5. Or 6, sorry, we'll do 6.
What group?
There's this old song from 2004, and I just recently listened to it, where they made a 6-7 joke. It was not funny. It's like, it's 6 going on 7 now. Shut up.
It's a song from 2005 though, so it's not like a 6-7 joke.
It's a song from 2004, actually.
Oh,
I think.
bad.
It actually might be 2000. I actually don't know.
Y'all might want to go ahead and get your stuff together because this will probably take us right up to time. So y'all might want to, everybody else might want to go check out your computers and stuff so we're not distracting them in case they go a little bit over. Y'all can leave it. I'll let you know when it's 9:50, but there's a good chance we'll be right there. Okay, you guys ready? All right, good.
Please, speed, I need this. Mom's got it homeless.
Right there.
I'm Kermit Clark. Oh, forgive me. Here's our design.
Shook hands. This is not.
Oh. Alright, so this is the challenge. It is to design a device that will catch crabs and sort them. The device must have a deck that is 4 inches above the ground. Both crabs have to come out of the area, but only one pre-specified crab can go up onto the ramp that has been selected. And there must be 3 joules of potential energy max coming from mousetraps, rubber bands, and gravity. And then the other constraints will be touched on later when we look at the legality of this.
Okay. Here is our isometric of the slide. We have, well, it's, as a lot of groups have said, very simple, but honestly, I think ours was competition. But, so we have our ramp, our wall. So here, we have an arm that will swing outward.
Hold on.
Oh, yes.
We're gonna have a story on the next slide. But
Yeah, we can see that.
as you can see, it has a bunch of different components that will successfully work together to complete the challenge, all kind of combining. And then the successful part will be duly noted later, like showed.
Alright, it's rubber band.
Yes. Okay, and then here's our storyboard, and he's gonna tell you about how it works, and I will show you with our
So here's our, well, this is how it's gonna be before we actually finish the mechanism. It will swing out here. It has wheels. You can kind of see it. I wish it was higher volume, but
You can see it here.
Yeah.
Let me just, we have the wheels on the end of our actual thing. And the axle is fixed, so it's like the wheels have a little piece here in the axle.
this will hopefully reduce friction. It will swing outward, and the prongs on either side right here. The prongs right here will be high enough only to catch the big crab, while the small crab will be too short to be caught by the prongs. It will hit the small crab away, while the prongs will carry the big crab and hopefully launch it up, and we have the walls there to stop it from going up. Before, okay, so to actually trigger, we have a
This cardboard piece, it'll be pushed down with a 1-finger push. So it'll be sitting right here. We have rubber bands, we put the rubber bands.
So, yeah, the way this is, well, where the energy comes from are these rubber bands that are around the axis. Hopefully
Our
they
actual dowels are 1/2 inch,
yeah.
but these are the
So-
sticks that were allowed.
The rubber band will be stretched, it'll want to unravel, and so will the arm. The arm will want to go in the arc.
And then we have all 3 of the rubber bands actually on there for energy, but for this case, we don't want to break the wooden things. So it'll be tensioned here, and then with a 1-finger push, we will push it down, and then the
because this little crab's not tall enough, the big fish won't catch it at all, and it will just hit this little crab out of the box. And then the big crab, it will catch on the edge of the claws with the actual pieces of plywood, and then it will scoop it up and throw it into the corner over here.
And these posts that the rubber band is wrapped around, they can be tweaked, they're just posts. We can move them.
So if we need to get more energy by stretching the rubber bands more, or if we need to add more rubber bands, we can also do that, which we'll touch on later when we get to analysis. All right, and then we have the actual crab wrapper. As I said, it's designed so that it will catch a small crab, grab a big crab, and kind of fling it up the ramp. And then we have the isolation, the different dimensions of it here. We originally put it as PLA, but we realized that was going to be way too much SciTech dollars to fit. So we decided to change into plywood and then hot glue the sections of the plywood together.
I think you're talking about wood glue now. We didn't think of that. That sounds really nice, actually.
So we'll definitely touch on that if we worried about money, but that'll be on the later slide. And then here are the parts of our design. So the main parts are obviously the deck and arm and then the actual crab grabber. Bottom. I don't know if you can see this, but we have the actual design on a piece of cardboard with a little dowel on the edge as a support beam, and then just a single dowel on the bottom of the middle. Basically, in the 1x3, it is exactly pretty much 1x3 with the edge of cardboard all the way to the edge here. And so we have all the different parts labeled and whatnot, and then like every single one of the elements. And then this is the legal slide. Obviously this is within the 1x3 rectangle. Literally big enough where that's the max that it would be as a